Good morning, everyone. After um, discussing average power, right, we want to discuss a bit what's called RMS value for circuit values. So RMS values, you could define RMS values for either currents or voltages. And in this lecture we will describe the point of RMS values. Why are they defined, and what's the logic behind them, and what are they used for? So the idea is that we discovered for general circuits, you discovered that, hey, the capacitor actually does not consume any average power, right? So P average for a capacitor, let me call it P average, or P, right, is zero. For an inductor, P average is zero. But for a resistor, the resistor does actually consume average power. Right? And we discovered that the formula for the resistor is, of course, this is of course in the case of sinusoidal steady state analysis. So this is sinusoidal steady state analysis, or what's called AC steady state analysis. So under that context, the capacitor does not consume any average power. However, what it does, it exchanges power. It sometimes consumes power, and then at other times it gives back power. So it's continuously taking in and giving back power, right? Taking in and giving back energy. That's its nature. That's the nature of reactance. Same thing with an inductor. It's continuously taking in energy and then giving back energy. But on average, it's not consuming any energy. It's not consuming any power. Power is just energy over time. Right? But the resistor, though, it does consume average power, and we found that the formula for the average power consumed by the resistor turns out to be Vm Im over 2, where Vm is the magnitude of the voltage applied across the resistor, and then Im is the magnitude of the current applied across the resistor. Right? So for a resistor, P average equals Vm Im over 2. And using Ohm's law, we can rewrite this. Ohm's law still applies, right? Vm equals Im R for the resistor. So I can rewrite this in two other forms. I can rewrite this as either half Im squared R, or Vm squared over R. So instead of I write Vm over R. So Vm squared over 2R. Okay. Now notice that this is for AC analysis. People noticed that this value for the average power, right? This is for AC sources. This value for the average power differs from the case where we have DC sources. When we have DC sources, we discover that the average power, which is the total power at any time, right, is just, let's assume we have a circuit with a DC source. So at steady state, when everything is stable, right, now that's the assumption that there was some capacitors or inductors that stabilized at steady state, but the sources themselves are DC, are not sinusoidal. They're not wiggling with respect to time. Right? So the average power in that case follows from the power law, right? It's just VDC, and then IDC. It's just VDC times IDC. Right? So notice it's different. DC analysis and AC analysis gives us different formulas for the average power. So we want to use this to define like an effective voltage or an effective current, right? That is going to give us something that's equivalent to the DC case. So I'm going to describe that in a bit. But the DC source's average power is just this, and then from Ohm's law I can rewrite this as ID squared R, and then VDC squared over R. Notice it's different. Here we have the extra 2, here we have the extra half, extra half, extra half. So we want to somehow roll in this extra half into the circuit variables in a way such that we get formulas that are equivalent to the DC case. That is the motivation, right? How to bring back the different formulas for the AC case in a form, put them back, rewrite them in a form that makes them match the DC case. So in a way, we were trying to kind of find a measure of effectiveness of a source at delivering power to a resistor compared to a DC source. That's the comparison. So we have the DC source. The DC source delivers power to a resistor using this formula, this formula, this formula. The question is, if I go away from a DC source into another kind of source, let's say an AC source, what is the effectiveness of that source at delivering power to a resistor compared to the DC source? Right? The effectiveness differs, right? So for a DC source, let's say I apply a DC source of 10 volts, right? I get this power formula. I apply a DC source I apply an AC source with a magnitude of 10 volts. The effectiveness is different, right? The effectiveness is half, because now I don't get Vm squared over R, I get half Vm squared over R. So clearly, depending on the form, the time form of the source, that the shape of the source with respect to time, the effectiveness of this source at delivering power to a resistive element varies. And we want to somehow measure that effectiveness. We measure that effectiveness by introducing the concept of RMS. So let me go give you a definition. So definition. Effective value of a periodic waveform. And we want to concern ourselves with periodic waveforms that just repeat themselves, like a sine wave or a triangular wave. Right? We want to concern ourselves with a periodic waveform. Right? We won't consider a general case where the waveform is just varying randomly with respect to time. We cannot define an effective value for that. What we can though do is, if we have a waveform that is periodic, a voltage or a current that's periodic, we can compare its effectiveness at delivering power compared to a DC source, right? We can compare that easily if the waveform, the time varying waveform, is periodic, right? So this can be applied to a periodic current or a periodic voltage. Right? So effective value of a periodic waveform is the constant value that delivers the same power to a resistor if the source is assumed to be DC, right? So let's say you have a periodic voltage source. So the effective value of that periodic voltage source is some constant voltage that delivers the same power to a resistor if we assume that source is DC. It delivers the same power of the AC source if we assume that source is DC, okay? So let's use that definition. So power, so we said the formula for average power, we want it to exactly match whether the source is AC or DC, or triangular, we want it to exactly match the DC case. In the DC case, what's the formula for the power? The formula for the power is I effective squared R, right? Let's say I want to find the effective value for a current waveform. It's the same for the voltage. For the voltage is going to be V effective squared over R. We want my average power to follow this formula. Okay, So let me write what the average power is. The average power for any waveform, any periodic waveform applied to a resistor, whether it's voltage or current. Let's take the case of the current. So it's going to be, what's the average power? It's just the instantaneous power, I square R. This is a power in one moment in time, integrated over the whole period, right? So this is the power in one moment in time, instantaneous power, integrated over the whole period from T0 to T0 plus T, right? This is the area under the curve. Divide that by the period, that gives me the average power. That's the definition of the average of a signal. Find the area under the curve, divide by the period. Right, so this is the average power, and this lets me easily derive the effective value of I, right? So I can, and this also repeats easily with respect to V. The V effective will be the same formula essentially, right? So I can rewrite this. So this is P equals, I can take R out. R is constant. I can always take it out of the integral. So I end up with P 1 over T, T0 plus T, I squared T dt times R. I took R out of the integral. So that means this whole thing now is I effective squared, right? So I effective, the effective value is just the square root 1 over T, 1 over the period, T0 over to T0 plus T, I squared T dt. Notice here we're taking the square of the signal, we're averaging it, and then we're taking the square root. So another way of that's why there's another name for the effective current. It's called the root mean square. We're doing three things. We have a signal coming in. We're squaring it first, and then we're taking the mean value, and then we're taking the square root. 3 steps. So that's why we call it root mean squared. And another more common, much more common term used to describe effective currents and voltages is what's called the root mean square. So we don't say I effective mostly. The term is used, but what's much more common is to say I RMS. RMS stands for root mean square. So the RMS formula is this: 1 over T, T0 plus T, I squared T dt. Right? And this is the same also for the VRMS, because I could get back the P formula and plug in V square over R and take 1 over R out, and I'll get the same value for the effective voltage. So the effective voltage, which I can call VRMS, is also square root 1 over T, T0 plus T, V square T dt. Okay, so those are the two general formulas for effective currents and voltages, and what's also called the RMS value. Now, what's the RMS value for a sinusoid? Right, a sinusoid is the periodic waveform of interest, right? Because it is the basis of AC analysis. We could do the effective value for other kinds of periodic waveforms, but the major one that we are basing all of AC analysis on is the sinusoid. So what's the RMS value for a sinusoid? Let's stick with the current case. For the voltage, it will be the same thing. So a sinusoid looks like this. It has a magnitude, and it has a phase, right? And then the period, we said, is going to be 2 pi over omega, right? We know that, right? We know that omega equals 2 pi f, so we end up with 1 over f, which equals t, right? So we know this. Okay, let's plug in. All we need to do now is to take this and plug it in the definition of the RMS value and integrate. So I RMS equals square root 1 over t, start from 0 to t, integrate over a whole period, and then I have Im let me call this I small m, Im squared cosine squared omega t minus theta dt. So I have a cosine squared m there. I have to go back to the identity. What's the identity? I have to define. So remember, we have those identities. Cosine. Let's say what's cosine 2 phi. Let's say what's phi? Phi is phi plus phi, right? So we know that identity. This equals cosine phi times cosine phi, which is cosine phi squared, minus sine phi times sine phi, which is sine phi squared, right? But we know, like, what I can do is that I can say cosine squared phi plus sine, what can I say? Remember the identity, the other identity, that cosine squared phi plus sine squared phi equals 1. This is also another basic trigonometric identity. So that tells me that sine, I want to write everything in the right hand side in terms of cosine. So that tells me that sine squared phi equals 1 minus cosine squared phi. So plug in this back there, I end up with cosine 2 phi equals, so this is 1 cosine squared, and then instead of, so let me write it down, cosine squared phi minus 1 plus cosine squared phi, I end up with 2 cosine squared. So I end up with essentially cosine squared phi, take the 1 to the other side, equaling 1 plus cosine 2 phi over 2. Right, so I just derived this basic identity. You should at this point be comfortable using that basic trigonometric identities that we derived at the beginning of the lecture, at the beginning of the course. Right, so let's plug that cosine square back inside the integral. Right, and let me take the constants out. I want to take the constants outside the integral. Right, so I end up with I RMS equals Im. I took Im out. So I have Im squared. I take it out. I square root it. And then I have square root of t over square root of t. So I end up with Im over square root of t integral from 0. Oh, so there's still a square root. Integral from 0 to t. And instead of cosine square, I put in its value, which is 1 plus cosine 2 phi over 2 dt. Right? And what is phi in this case? Phi in this case, the angle is omega t minus theta. That's what's inside the cosine, right? So I just put 2 omega t minus 2 theta. Right? Let me take the 2 out of the integral. So I take the 2 out of the integral, and I take it after the square root. I end up with square root of 2 here. Okay. Now this integral is interesting. So we're integrating a constant, and we're integrating a cosine. We can do this integral if you want. You can do it, but we want to use a very basic properties of sinusoidal functions when you integrate them over a single period. This very basic property is as following. Integration, when you integrate over a period, integration is the area under the curve, right? That's the definition of the integral. That's one way to look at the integral. Well, for sinusoidal signals, if you look over one period, across one period, it's clear that the area under the curve is always 0, right? I have some positive area here, and then I have some negative area here, right? Because it's underneath the x-axis. So the area under the curve will always be 0. The positive area is going to always cancel the negative area if you're integrating across a whole period. So if you integrate any cosine or sine across a whole period, you end up with 0. Right? Even if you have combinations of cosines and sines all at the same frequency, if you integrate over a period or the period of those cosines and sines, you will end up with 0. So integration of this term is going to give me 0. What about integration of the 1? Well, integration of the 1 is going to give me t, but then t is going to be evaluated from 0 to t. So this whole thing is going to turn up to square root of t. which cancels with this thing, and I end up with I RMS equals IM over square root of 2. That's the RMS value for a sinusoid. Same thing for VRMS. It's going to be, you can do the same exact calculation. It is the same exactly. Instead we have VM instead of IM, and we end up with VRMS equals VM over square root of 2. So going from the magnitude, from the peak of the voltage and the current to the RMS value is just a matter of factoring by square root of 2. Right? And it's very common. So remember when we represented phasors, using magnitudes. So for example, the wall outlet, you can represent it as this way, right? The voltage of the wall outlet, you can represent it as, right, as a phasor, which is 170, 0 degrees volt, for example. And here we are representing it with the magnitude of the voltage. But then also I can represent it using the RMS value. It's very common in AC analysis to represent in the phasor representation to put in the RMS value rather than the peak value. So I could represent it as 120. 120 is the RMS value, right? And then I should just say volt RMS. Okay. So my unit here is volt RMS. This doesn't always happen. Sometimes people just put volt, but they tell you or that this is the RMS value, not the peak value. They tell you that, or the convention is that this is the RMS value. So whenever you're reading material or papers or textbooks, you have sometimes to be careful about what the explicit or implicit assumption is. Sometimes they explicitly say it's RMS, right? So it's volt RMS. Sometimes they don't, but it's from context you should know. Because for example, in power systems, they typically always give you, when someone tells you what the voltage of coming from the wall outlet is, they typically give it to you in RMS. Okay, so you have to be careful there. It can be a little bit confusing. I like to just, even when I write stuff for myself, I like I like to write RMS. Right? Sometimes people don't adhere to that always, but I always like to do that. So if I'm talking about an RMS current, I say amps RMS, an effective value. If I'm talking about an RMS voltage, I say volt RMS. That's something I like to do. Okay. What's now with this concept of the RMS value? Let's revisit the formula for the power. So the formula for the power is what? Is VM IM over 2 cosine theta V minus theta I. Right? And we said, hey, the VRMS equals VM over square root of 2. What does that mean? That means that VM, the magnitude, equals square root of 2 VRMS. And same deal, IM is going to equal square root of 2 IRMS. So I can plug those in here, right? So I end up with P equals square root of 2 IRMS, square root of 2 VRMS. I end up with 2 VRMS IRMS over 2. 2 cancels with 2. And I end up with this formula using the RMS values. What about the case where we have a resistor, meaning in the resistor, the voltage and the current are in phase, so we have cosine 0, which is 1, right? We end up with P equals VRMS, IRMS, exactly the same equation as the DC case. And I can plug this in. And Ohm's law still applies to RMS, right? Because Ohm's law states that what? VM equals R IM, right? Divide everything by square root of 2. You end up with VRMS equals RI RMS. So clearly, even with the RMS values, Ohm's law still applies. So I can rewrite this as either VRMS squared over R, or if I plug in the value for VRMS, I end up with I RMS squared times R. So this is what RMS gives you. It allows you to write the power equations for a resistor in a form that's exactly equal or exactly equivalent to the DC form of the equations. Okay, so that's why they are so useful. Okay, so this is the RMS value for us. This is how you calculate the RMS values of sinusoids. It's easy. You just multiply by 1 over square root of 2. You multiply the peak or the magnitude by 1 over square root of 2. What about cases where the periodic signal is not a sinusoid? Well, we can calculate that too, but we have to revert back to the integral equation. Right, so let's do an example from the textbook. What if this is the form of the periodic waveform? So I have a waveform that looks like this. It's a square waveform, I guess. We can call this a square waveform, right? And it dissipates. So this is, let's say, a current, and this current is passing through a resistor. What's the RMS value of this current? So it goes from, I think, -4 to 4 amps. And the period is, half period is 2, the full period is 4 seconds. So this is the full period, 4 seconds. After 4 seconds, the signal starts repeating. So it repeats itself here and it repeats itself here. Okay, so we have just to plug in the integral formula. I RMS equals square root 1 over 4. And then we have to integrate this. Notice you can always divide the integral. So if I have x of t integrated from a to b, I can always divide it into subintervals. So I can go a to c x of t dt plus c to b x of t dt. This is a basic property from calculus, right? I can always divide the integral over subintervals, right? And those subintervals add up to the whole interval. This is a basic property of the integral from calculus. Okay, so I can integrate from 0 to 2 and then integrate from 0 to 4. I want to do that. I want to separate the integral into subintervals because the form of the equation inside the integral varies depending on what interval I'm in. So this allows me to plug in the various equations for the various intervals inside the integral. So I can first integrate from 0 to 2. Inside that interval, the value of the function is 4. So I take 4, square it, dt. And then I integrate from 2 to 4, the value of the equation or the function in this interval from 0 to 2, from 2 to 4 is -4. So I take -4 and I square it, dt. Luckily, in this case, the squaring is going to get rid of the minus sign. So I end up with, let me do this. So I end up with 1 over 4. I can take so -4 squared turns out into 4 squared. So I can take the 4 squared out. So I end up with 4 squared. And then the integral becomes 0 to 2 dt plus 2 to 4 dt. Right, I can easily evaluate this. This is just t evaluated from 0 to 2. This is just t evaluated from 2 to 4. So this is going to be 2 minus 0, 2, and this is going to be 4 minus 2, which is 2. So this is going to give me 2, and this is going to give me 2. Sum them together, I end up with 4. So RMS is going to be 4 squared over 4 multiplied by 4. 4 cancels out. 4 squared under square root becomes 4. Okay, so the current now is going to be 4 amp RMS. Okay. I could have, just not given you 4 and minus 4. I should have just said the magnitude is A and minus A. And you could have derived the symbolic formula. Perhaps that would be a good exercise for you to do. But I mean, in this example, I just gave you the values, the magnitudes. Okay. All right, let's do the other example. It's a little bit more complicated waveform, but it's the same thing. I mean, it doesn't change. The method that you use is the same method. Okay. So let me draw the second more complicated waveform. So from 0 to 1, we have a ramp, and the ramp ends here at, oh, this is a voltage signal, by the way, ends up at 4, and then we go down to 0 after 1. And then from 1 to 2, we stay at 0, and then from 2 to 3 seconds, we ramp down, and then we go to 0. Right? This is the period. After that, the signal repeats. This is how the signal looks in a single period. So after that, the signal is going to repeat. It's going to go up, go down, 0, go down, ramp up, and then up, right? And then it's gonna keep repeating itself, so on and so forth. And the same thing here, it's gonna be repeating itself, right? But this is how it looks like in a single period. So we can write it down in piecewise function form by writing that its functional expression in each of the intervals. There are 3 intervals. There are intervals from 0 to 1, and then there's from 1 to 2, and there's from 2 to 3. And you know how to do this. I mean, you in calculus 1 and 2, right? So this is a ramp, right? So this is a function that has a slope, right? It has a slope of what? 4 over 1, which is 4. So it's a linear function with a slope of 4. So this is going to look like 4t. What about the initial condition? With at t equals 0, this ramp equals 0. So this is correct. At t equals 0, this thing equals 0. What about from 1 to 2? That's easy. That's 0. Okay. A little bit trickier is 2 to 3. This is still a line, a linear segment. So this is a linear function. What's its slope? The slope is delta y over delta x. What's delta y? Delta y is just also, so this is minus 4 here. Delta y is just minus 4, and delta x is 3 minus 2, which is 1, so the slope is minus 4. So this is a linear function that's going to look like this, minus 4. You know how to write a linear function. If you have a slope, the linear function is just the slope times t, plus some constant, which we have to determine. Right? But the slope is going to be minus 4, so this function is going to have minus 4t. What about the constant that we have to determine? Well, I mean, we have to look at the initial condition. So what happens when t equals 2? When t equals 2, this gives me minus 4 times 2 gives me minus 8. But I know that this curve at t equal 2 is equal to 0 exactly. So how do I make this equal to 0 at t equals 2? Well, I need to add 8, right? So I end up with, if I plug in t equal 2 here, I end up with minus 8 plus 8, 0, which is exactly equivalent to what the waveform is telling me. Okay, so this is the functional form of the voltage, and all we have to do now is apply the formula. So V RMS, and let me do something. I don't want to keep writing the square root. Let me take the square roots of both sides of the formula. So I end up with V RMS squared. I'm going to solve for V RMS squared. So that equals 1 over t. What's t in this case? 3 seconds. And then I need to integrate over 3 intervals. Right? So I take the integral from 0 to 1. And from 0 to 1, the form of the function is 4t. So I end up with 4t squared dt plus the integral from 1 to 2. And I have 0 squared. Right? This cancels out. Then I go from 2 to 3. And I have 8 minus 4t squared dt. Right? And I keep doing the math. So it's 1 over 3. I take 4 squared out, so it's going to be 16. I want to integrate t squared. T squared is just t cubed over 3, and I need to evaluate that from 0 to 1, plus, I want to square this now, which is going to make it a bit, let me square this face first, right? So it's going to go 2 to 3, and I end up, well, let's square 8. Squaring 8 is 64. And then squaring the other term is going to be plus 16t squared, and then minus 2 times 8 times 4. So it's going to be minus 2 times 8 is 16. 16 times 4 is 16 times 2 is 32, times 2 is 64, so it's going to be 64t dt. I just squared that expression. Right? Now I need to find that integral. So this is going to be 1/3 16. So this is going to be 1/3 minus 0/3. So it's going to be 6. I end up with 1/3 here. So it's going to be 16/3 plus, okay, and let me integrate this expression. So this is going to be 64t plus 16 t cubed over 3. I'm just applying integration term by term, and this is minus 64 t squared over 2, applied from 2 to 3. Okay, and let me simplify here. Divide 64 by 2, I end up with 32. Yeah, I mean it's cumbersome, but that's all this is. I mean, just do the calculations. It's going to be 16/3 plus 64 times 3. So I need to plug in 3 and 2. So let me plug in 3 first. So I end up with 64 times 3 plus 16. 3 cubed is what? 3 cubed over 3 is just 3 squared. 3 squared is 9. So it's going to be 16 times 9 minus 32 times 9. Right? I plugged in the 3, and now I need to plug in the 2. So I'm going to end up with minus 64 times 2, which is 128, minus 16 2 cubed over 3, 16 2 cubed over 3, and then and then minus becomes plus 32 2 squared, which is 4. So yeah, so multiply all of this, sum them up together. If you go to MATLAB and do this, or use a calculator, you'll end up with 3.556. So VRMS is just going to be the square root of 3.556. So VRMS is just going to be equal to 1885 VRMS. Okay, and like I said, you can put in the unit as volt RMS, or you can omit it, it's fine. It depends on the context. I prefer to always put the RMS so that I'm not confused when is a value an RMS value or a peak value or a magnitude value. Okay, let's jump now into the next concept we want to discuss in this lecture. Nothing new here. It's just a matter of adding or introducing you to new terminology. We will not be deriving any new facts or deriving any new equations. All right, so this is just a matter of terminology when it comes to AC power. So going back to the power equation, as it's described for the case of RMS value, we said this is going to look something like this. Cosine theta V minus theta I. Let's examine carefully the constituents of this equation. So this has this part. This is a part that has units of power, watts, right? But this is the part that carries the units, because V times I is just V voltage amps, which is watts. This part is unitless. It's kind of like gives you a number from 0 to 1, right? It gives you a number from -1 to 1, right? So it's just the cosine, right? It gives you a value from the cosine. This is not the cosine. The cosine looks something like this. Okay, its extent is from -1 to 1. So this seems to be a unitless factor from -1 to 1. Okay, so it's the terminology is this has units of power, but it's not the actual average power. It's the maximum possible average power. You get the actual average power only after multiplying it by a factor. and this factor depends on the angle between the voltage and the current, right? And its factor is from -1 to 1. So those phrases that I'm saying will give you an indication of what I'm going to define next, right? So this is what's called, just VRMS IRMS is what's called the apparent power. It is a power because it has units of watts, volt times amps, but it's not the actual average power. It is the apparent power of the system, right? And it has units of volt amps, right? So to distinguish this power from the average power, which is the real power, people use units of VA for it to distinguish it from the average power. So when I'm talking about average power, I say 50 watts. When I'm talking about this is average or real. When I'm talking about apparent power, although the units are still watts, to distinguish the two, I say 50 VA. This is the unit that I use for apparent power. Right? So I say 50 VA. It's the same thing, V times A is watts, but the convention is to call apparent power VA. Use units of VA for apparent power so that you can distinguish it compared to real or average power. Okay, so we established VRMS, RMS is the apparent power. This thing here, this factor from -1 to 1 is what's called the power factor. Okay, so and from this formula, it's clear that the power factor is just the P average over VRMS IRMS. That's what it is, right? And which is equal to cosine theta V minus theta I. Okay, so those are the two concepts that we're introducing: the apparent power, let me call it P apparent, which is just VRMS IRMS, and then the power factor, which is P average in this case. When I write P, I mean P average over VRMS IRMS, or cosine theta V minus theta I. Okay. Of course, I can rewrite theta V minus theta I. Instead of theta V minus theta I, can write cosine theta ZL, right? The angle of the difference between the angle of the voltage and the current is just the angle of the impedance. Why? Because the impedance is V over I. So this is like V magnitude theta V over I magnitude theta I. So the magnitude of the impedance is Vm over Im. The angle of the impedance is theta V minus theta I. Right? So you can look at theta V at minus theta I as just being the angle of the impedance that this voltage. So if I assume this voltage, some voltage source is applied to some impedance, right? This impedance is going to cause an angle between the voltage and the current, and this is the angle of the impedance, right? So that's why theta V minus theta I is also called the, or theta ZL is called the power factor angle. So this is the power factor angle, its cosine is the power factor. Okay. All right, so nothing new here, just new terminology. So for a resistive load, what's the power factor? Well, theta V minus theta I is 0, right, for resistive load. So it's cosine 0, so the power factor is 1. For a reactive load, just a purely reactive load, just an inductor or a capacitor, or a bunch of inductors and capacitors, well, the power factor is cosine theta V minus theta I. For a reactive load, either a capacitor or an inductor, the voltage is always leading or lagging, or the current is always leading or lagging the voltage by 90 degrees. So this is going to be, some cosine plus minus 90 degrees, right? We established that. The angle for a purely reactive element, the angle is going to always be either plus 90 or minus 90. The impedance is either j omega L, which is plus 90, or 1 over j omega c, which is minus 90 degrees. Right? So, but it doesn't matter. Cosine plus 90 or minus 90 is 0. So the power factor is always going to be 0. Okay. So the power factor is 1 for a purely resistive load or element. It's 1 for a purely resistive element. It's 0 for a purely reactive element. What happens if we have a mixed element? An element that has resistors, capacitors, resistor, inductor. It's mixed between the resistance, and it has a mix of resistance and reactance. In that case, if I draw the phasor diagram, right, the current is always either going to be lagging or leading, right? So cosine theta v minus theta I will be between minus 90, will be between minus 1 and 1, right? Because theta v minus theta I, depending on the exact load, will be between minus 90 degrees and 90 degrees, right? So in the case where we have mixed elements, resistive and reactive components mixed together, the power factor, this is the power factor, is going to be between minus 1 and 1. Okay. Typically, we don't give negative power factor. Typically, we just give positive power factor. But then we say, right? And there's something curious here, actually. Let me restate this. Let me restate this way. So what I claimed is kind of like wrong a bit here. Why is it wrong, by the way? Cosine, this is correct if I'm dealing with cosine in general. Cosine in general, okay. So I made a mistake here, actually, so forgive me. So let me kind of rephrase. It's not 1 and minus 1. It's 0 to 1. Why? So it's true that cosine goes right from 1 to minus, right? But the issue here is that I'm taking the cosine of theta v minus theta I. We said that the maximum, so if I have v, the maximum that could happen is that if I have a reactive load, capacitor or inductor, what could happen is that the I could be at maximum at minus 90 degrees or at plus 90 degrees. That's the maximum. But if I string in a resistance with the reactive element, I end up with something like this. Right? So the extent, so theta v minus theta I is always going to be between minus 90 and 90. Right? So if I take the cosine of this, so I end up with cosine theta v minus theta I, this becomes cosine minus 90 and cosine 90. Cosine is even, right? So cosine minus 90 is equal to cosine 90, right? All right, so this is going to be what I'm trying to say is that theta v minus theta I is going to be limited to this range, and in this range, the cosine is always going to be larger than 1. This is the right way to look at it. So the cosine of theta v minus theta I, which is the power factor, will always going to be larger than 1. Okay, so the power factor is always going to be larger than 1, and it will be, and here's the tricky thing. If the current is lagging the voltage by a certain angle, or it's leading the voltage by a certain angle, we will get the same power factor. Power factor by itself does not distinguish, right, whether the current is leading or lagging. Why? Because cosine theta v minus theta I equals cosine theta I minus theta v. It doesn't matter. Even if I have a negative sign here, the cosine doesn't distinguish the negative sign. It gives me the same reading. That's why the convention is not just to give power factor. The convention is to give the power factor and state whether the power factor is leading or lagging. And when we say leading or lagging, we are referring here, what's leading or lagging? What we're referring here is the current phasor with respect to the voltage phasor. It's the current that is either leading or lagging. It's the voltage. So we're talking about, when we say power factor is leading or lagging, we're talking about the current. What does the current phasor do? Okay. For example, current for an inductor. So I for an inductor is V over Z, right? Which is V over J omega L. So for an inductor, the current is lagging the voltage by 90 degrees. Okay. And then for a capacitor, I equals V over Z. 1 over Z is J omega C. J omega C V, right? So that's for the case of a capacitor. For the case of the capacitor, the current is leading the voltage. Okay, so we will go through some examples, but that's, you have to be careful with the terms leading and lagging. They refer to the current leading or lagging. Okay, so let's do, I want to do an example. Let's do an example. Right. So let's say we have some kind of industrial load. And this is the typical way in the industry that loads are described in power systems in general. So we say, hey, this industrial load, let's say a factory or whatever it is, consumes 88 kilowatts, right? But typically that's not enough. Typically people are not just satisfied with telling you, hey, how much average power this load is consuming. They give you more information. They say this load consumes 88 kilowatt at a power factor of 0.707 lagging. Okay, so once you see lagging, this is probably an inductive load. Right? And most loads are kind of inductive. It's more common to find a lagging load rather than a leading load. So this load consumes blah, blah, blah from a 480 volt RMS mains. Okay, so let me kind of like reiterate this point here, right? So we said, hey, this is VL, the load, it's a phasor. We say the load is lagging, meaning that the load is behind, that the phasor representing the current is behind the voltage, right? And then VL over IL is just going to be magnitude of Z times theta V minus theta I, right? The angle is theta V minus theta I. It's the, right? Because V is in the numerator, IL is in the denominator, right? That's how we add angles up. Right? So theta V is minus theta I. So if I look at Z, right? And typically this impedance I get with a positive angle here because the current is lagging. Typically I get a positive angle when I have something with a mix of an inductor and a resistor. Right? So if I look at the complex plane, look at the value for the impedance in the complex plane, typically when R plus JX, when the angle is positive, I'm here, right? Because I'm here, I have an inductive load, right? When the angle is negative, I'm here. And in this case, what I have is the capacitor. Oh, I made a mistake here. Again, right? Typically, the angle of the impedance, the maximum angle, so between the voltage and the current, is always going to be 90 degrees, right? We've established that, right? Because the impedance, the maximum angle could be either inductive j omega L or 1 over j omega C, which is minus j 1 over omega C. Whenever we have resistance, we get a mix, right? So we get like a smaller angle than 90 degrees, right? Because if I look at the z-axis, if I look at the impedance in the complex plane, the impedance is always going to be, j omega L, that's 90 degrees. But then when I add some real part, some resistive part, I always get an angle that's less than 90 degrees. Or I could start with an inductive capacitor, which starts at minus j over omega C at minus 90 degrees. If I add a resistor, I always reduce my angle. The maximum angle of an impedance will always be 90 degrees. So if I plot the impedance on the complex plane, it always be in this regions. And the region from where the angle of the impedance is from 0 to 90 degrees is going to be inductive load, where the angle is going to be from 0 to minus 90 degrees is going to be capacitive load. So whenever here I see it's going to be, when I see a power factor that is lagging, that tells me that the voltage is behind the current, right? So when I divide the voltage over the current, I get a positive angle for the impedance. That tells me that the load is inductive, because the voltage, the current is lagging the voltage. Okay. Now they give me in this example further information. They say, hey, this utility is providing this customer with this amount of power, but there's a transmission line in between. You're generating the power and you're transmitting it over a transmission line, and then it reaches the customer. And this transmission line is modeled as a resistance. So this transmission line has a resistance, what's called a line resistance of 0.08 ohms. It's a small value, but it's there nevertheless. Okay, so what is the power that the utility needs to generate? Right, and we will discover that the power factor plays a role on this in determining how much power the utility needs to generate. Intuitively, you could think that, hey, the utility needs only to generate 88 kilowatts. Yeah, but that's not the case, because there is a transmission line. So some power the utility generates will be lost in the transmission line, in this resistor that represents the transmission line, right? So the utility in general needs to transmit more than 88 kilowatts. Some of it is going to be lost in the transmission line, and then finally 88 kilowatts reaches the customer. Right? How much is lost in the lines is going to be heavily dependent on the power factor. Okay. So let's draw this as a circuit. So this is a utility, it's just a voltage source. The transmission line has a resistance of 0.08 ohms. It's small, but it has a value, non-finite value. And this could represent like maybe, I don't know, 50 miles of transmission line. We don't know, right? We just give you the lump value, which is 0.08 ohms. Right? And this is the load. The load consumes an average power of 88 kilowatts at a power factor of 0.707, lagging. Okay, so what's the power? So the average power generated is well, first, from the lowest perspective, what is we have the power factor, we have PL, right? So what we can calculate, we want to calculate how much current is going through the circuit, is supplied by the transmission line. So we have the basic equation, PL equals V RMS I RMS cosine theta V minus theta I, which is the power factor we said, right? So we can solve for I RMS, that equals PL, which is given, over power factor times V RMS. We have everything else, right? We know that we're consuming 88,000 watts. Power factor is 0.707 and the voltage is 480. Do this calculation. I end up with 259.31 amps RMS. Okay. So in this case, what is the power that the source needs the utility needs to supply? It's the power, this same power, 88 kilowatts, the power that's consumed by the load, plus the power that's consumed by the transmission line. And now that we have IRMS coming from the utility, we can calculate easily the power lost by the transmission line. So P supply, this is supplied power, is just equal to PL plus the power lost in the transmission line is just I square R, right? That's it. So it's going to be 0.08 times IRMS squared. So this is going to be 88 kilowatts plus 0.08. We calculated IRMS already. It's going to be 259.31 squared. Okay. So the power consumed by the load is 88 kilowatts. The power lost in the transmission line, if we calculate this, is going to be 5.38 kilowatts. So the utility needs to provide 93.38 kilowatts so that the load can consume 88. The difference of 5.38 is lost in the transmission line. Okay. Let's assume like this utility came back to this customer, this factory, and said, hey, listen, your power factor is lagging too much. It's causing me to lose a lot of power in the transmission line. I'm going to fine you. If I'm going to have you pay a fine or pay extra rate unless you can improve your power factor. And let's say the people designing the factory, working on the factory, do a bit of tweaks in the way they extract power from the utility, and they improve the power factor of this load. They improve their machines or whatever, so that the power factor now is improved to 0.9 lagging. How will that affect the power that the utility needs to deliver? Well, we have to just redo the calculation. IRMS now is going to be PL over power factor VRMS. So it's going to be 88,000 over 0.9 instead of 0.707, 480. So IRMS now is going to be 203.7 amps. Notice the current required to be supplied from the utility is less now, just by improving the power factor. So it seems like what I'm trying to say is that higher power factor or power factor closer to unity is better. Right? So in this case, what is the power that needs to be supplied from the utility? Well, it's 88 kilowatts, and the loss in the transmission line is now 0.08 times 203.7 squared. So this is, okay, this is plus, not equal, sorry. So this is 88 kilowatts plus 3.32 kilowatts. Notice the loss in the transmission line now is less. Only 3.3 kilowatts is lost in the transmission line versus previously 5.38. So now the utility needs only to supply 91.32 kilowatts versus 93.38. And that improvement, nothing happened. The utility did not improve the transmission line. It did not go out and change the transmission line to a transmission line that has less resistance. That's too expensive. It just, what happened is just that the power factor was improved at the load. Okay, so power factor has an economic impact. That's why it's a factor that's very prominent in studying power systems. Right? Utilities typically insist that large industrial institutions like factories or large municipal loads work on improving their power factor. Okay, and typically power factor of 0.9 lagging or better is what utilities insist on. If your power factor is less than 0.9, you typically would be penalized by having to pay a higher rate. Okay, There are ways to improve power factor if you have a certain circuit that has a bad power factor. And when you improve power factor, this in the literature or in the industry, this activity of improving power factor is called power factor correction. This is something that you will hear all the time if you decide to go and study power systems in detail. If you go into the power systems space, you hear about power factor correction all the time. All right, I guess we will continue next time. We will start talking next time about the concept of well, we will touch upon power factor correction, but we also want to we want to introduce the concept of complex power. All right, we'll start that next time. Thank you.